You are traveling through another dimension. A dimension not only of sight and sound, but of light itself, where perception is constructed and reality is filtered. Distances can stretch or collapse, all at the command of a single parameter. As we cross the line between what is seen and what can be seen, here, focus is not given, it is found. We cross the boundary into the focal plane. Hello everyone, I'm Chris, a machine vision sales engineer here at Edmund Optics, and this is Byte Size. This is the part 2 of our series on the interaction between sensors and imaging optics. If you're new here, I highly recommend checking out our first entry. A masterpiece. The link is below. Now, let's dig in. Our topic today, focal length and magnification. Before getting into the meat and taters, let's talk definitions. Focal length is a fundamental lens parameter that describes how much work is done to the light hitting the lens. If the lens has a long focal length, this indicates that the light is being bent gradually. There is not much work being done to the light. On the other hand, if the lens has a short focal length, then we know the light bundles are being bent at sharper angles, and a lot of work is being done to the light. In a practical machine vision sense, longer focal length lenses have smaller fields of view, while shorter focal length lenses have larger fields of view. While the conventional way is to refer to the focal length in millimeters, this can be difficult to understand from a field of view perspective. What you should keep in mind is that the angular field of view and the focal length value in millimeters scale linearly. For example, on a 2/3 inch sensor, this 35 millimeter lens has an angular field of view of around 14.3 degrees. If we shorten our focal length by about half to 16 millimeters, our angular field of view expands to 30.9 degrees. Now, if we repeat this again with an 8.5 millimeter focal length lens, we'll see the same, with this having around 60.6 degree field of view. Now, if we want to tie it all together, consider what we covered in our first episode this season. Sensor size. If we take the ratio of our sensor size and our field of view, we get, drum roll please, our magnification. When we hold our working distance and our sensor size constant across these three lenses, our magnification varies significantly. But what impact does this have on our system? Well, when we have a low magnification and therefore a larger field of view, we see more stuff. But we see this stuff less clearly. And now you're asking, Chris, with all of your optical knowledge, please tell me, why does this matter? Well, let's pop over to the lab and see this in action. Welcome to the lab! In this corner, a 35 millimeter lens with a lean angular field of view of 14.4 degrees mounted on a camera measuring in at 2/3 inch and 5 megapixels, part number 85-869. And in this corner, the camera that needs no introduction, except for this one, a camera measuring in at 2/3 inch and 5 megapixels coupled with a lens measuring in at 12 millimeter focal length with a hulking angular field of view of 38.8 degrees, 63-778. Now, let's fix our working distances at, say, 400 millimeters and take a look at our images. As expected, our 12 millimeter lens has a significantly larger field of view. Here, we have a horizontal field of view measuring in at 300 millimeters, while over here on our 35 millimeter lens, this is only 94 millimeters. That's a difference of almost 3 times. But what about our image quality? Like I had mentioned, our 12 millimeter lens sees significantly more stuff, but comparatively it sees this stuff less clearly. Now you're probably asking, Chris, if we back our 35 millimeter lens up so that it has the same magnification as our 12 millimeter lens, our images should be identical, right? And I'd say, wrong. While I could quantify these differences in resolution, that's for another episode on resolution. As I mentioned in the very beginning, longer focal length lenses inherently do less work on the incoming light when compared to a short focal length lens. This means that longer focal length lenses typically provide higher resolution images than compared to their shorter family members at the same price point. You just need to be able to back a bit further away from your object. To a point. But what does all of this mean? Well, when building a new machine vision system, I always recommend trying to get as close to a 4:1 working distance to field of view ratio, or as I like to call it, the golden ratio. That's where you get the most yams for your clams. Always keep in mind, everything is application dependent. Ultimately, the best lens is the one that works for your application. Thanks, cadets, for traversing the optical space with me today. If you have any questions, reach out at edmondoptics.com. We have real live engineers available 24/7 to address your imaging needs. As always, I'm Chris Razzie, and this has been Byte Size.